Welcome people, and welcome back to Kevin Does Physics. Today, in our second video ever, we are going to be looking at topic 3.4, which is all about materials. So yeah, let's get into it. 1 minute. Yeah, okay, so these are the formulas we get given in the formula booklet for springs and materials. F equals kx, which is Hooke's law, then equations for storing energy in springs, the formula for stress, the formula for strain, and the formula to find Young's modulus. All of these will be explained in more detail in a minute. So, deformation. There are two main types of deformation: elastic deformation and plastic deformation. Before we can look at these types of deformation, we need to know about forces. So, there are two sort of main forces. You can have compression, where something is squashed. This may be, I don't know, let's say, when you, I don't know. If you get a water bottle and you sort of squash it, you're sort of compressing it, but that's probably not the best explanation. Tension is the act of stretching. So if you get sort of a rubber band and stretch it, that would be an example of the rubber band would then be in tension. Forces between individual atoms are of course small, but because there are many, well, you know mole is 6 point something times 10 to the 23, so many atoms in even a small amount of object, we actually, even though the individual forces are 1/whatever of a Newton, to actually deform a whole object, we need a fair bit of force. If you apply a force to an object and it squishes, and then you remove the force from the object, there are two things which can happen. The first option is it goes back to its original shape, and this would be an example of elastic deformation. For example, if you pull a rubber band, and then you don't snap it, but if you pull a rubber band and then let go, it will basically be the same as the rubber band before you stretched it. But if you, like me and like taking apart pens, and you know the spring in the pens, if you pull it really far, it won't sort of collapse again, and that would be an example of plastic deformation. In most cases, when sort of designing bridges or leaf springs on cars, we always want to be working within the elastic range. Yeah, tensile forces cause tension and compressive forces cause compression. Pretty simple. Really just to note, when using formulas, tension will always cause a positive extension. Basically, things being stretched is a positive extension, and things being compressed is a negative extension. When stretching springs, we can plot force against extension on a force extension graph. You may notice that the independent and dependent variables on this graph are switched to their normal. That is because we can, and of course this works with formulas such as f equals kx, because f over x equals k. So the gradient of a graph like this in the elastic limit would obey Hooke's law, which we'll be onto on the next slide. There are many important points to pay attention to on this graph. The point where the graph has a constant gradient and obeys Hooke's law is the elastic range, and the point at where it stops behaving fully the point where it stops obeying Hooke's law is called the limit of proportionality. Then for a while, it will still extend and behave elastically up until its elastic limit, which is quite close to the limit of proportionality. Finally, then as you apply more force, it will behave plastically before eventually failure happens and it snaps, which is bad, I guess. See you in a minute. Okay, welcome back, and on to the next slide. Hooke's law. So, I don't know who Hooke was. I always try and get you a bit of background on these scientists. Hooke was a guy, and, well, he proposed that force times by a spin constant, or force, I've said that wrong. Force equals extension times by a spring constant, and the spring constant isn't a property of a material, it's a property of a spring. So every spring will have its own spring constant. Yeah. Work done when stretching a wire or stretching a spring, or when stretching basically anything. If you think about our force times by extension graph, basically, the area underneath that graph is the energy which has been put into the spring to make it stretch. Of course, during the elastic range of your spring, all this energy is effectively stored and can be later released. From that graphical representation, E equals half Fx, where F is force, or by then subbing in Hooke's law, we get E equals half Kx squared. The difference is when we have plastic deformation, and this is when the spring will not go back to its original size. So, to think about it, the area under the graph is still the total energy put in to make the spring move. If you then think about the top line on this graph being the loading graph when we're adding mass to the spring, and the bottom line when we're taking it away, the area trapped in between these two lines is energy lost into heat produced in, well, this is in case of rubber bands, so yeah, that is lost energy, and the area underneath the bottom line is the energy which is still in the plastically deformed spring. Of course, this graph only works if you've plastically deformed it but not brought it to failure. On to Young's modulus. Young's modulus is an intrinsic variable. This means it does not depend on temperature, it does not depend on pressure. It's quite like resistivity in that sense. To calculate Young's modulus, we use stress over strain, and stress is force over area and is measured in newtons per meter squared, and strain is measured, well, strain is a measure of extension over original length, and because those are both per meter, the units cancel so there are no units. A Young's modulus of a material is often going to be quite large. If measured in pascals, it's often going to be around gigapascals in size, so times 10 to the 7 times 10 to the 8, quite large. To calculate Young's modulus, we have basically, what we do is we plot a graph of stress against strain for a material which you've been adding weight on, and then the gradient is Young's modulus. Of course, this only works whilst the material is behaving elastically. And the final part for today's video is ductility. Ductility is a property of a material such as malleability or tensile strength. And ductility is the ability to draw a material into a wire. So basically, if you have a material, let's take a pen I have here, and stretch it, is its ability to get thinner. A ductile material would be able to take a lot of strain for a small amount of stress. So if we go back to the previous slide, we know that strain is extension over length. So basically, a ductile material is a material which for a little force will stretch a lot. So, for example, a rubber band is going to be reasonably ductile. On the contrary, a brittle material... No, a rubber band is not a rubber band is a brittle material because it stretches elastically and then fractures very quickly. A ductile material will have a small elastic limit, and then you'll be able to stretch it for a very long time plastically before it snaps. Thank you for watching, and goodbye.